All right, so we just got done in my previous video talking about the chemical and physical properties of matter. So now we're going to go into chemical and physical changes of matter. So if you remember, matter cannot be created or destroyed, but it can change forms. All right. So when we talk about a physical change, we're just going to see um, a change where the substance is not changing. So like tearing a piece of paper in half would be a physical change. Whereas a chemical change, we're going to see a chemical reaction. And then when that chemical reaction occurs, we've created a new substance. So looking at these things here, physical changes are pretty simple. They're pretty easy to observe, kind of like physical characteristics or physical traits or properties, I should say. Changes in the size, shape, or the state of matter. So when I say the state of matter, we're talking about going from solid to liquid to gas with a water molecule. With physical changes, the identity of the substance will always remain the same. Okay, so great example is water. When you have you put some ice into a pot. You put the heat on the burner. You turn the heat up. The ice starts to melt. It goes from a solid to a liquid. Okay. If you keep it there and it starts to boil, that liquid then becomes a gas. You have not, even though that water has changed forms or the state of the matter, you have not changed water. It's still water, it's just in different forms. That's a good example of a physical change. Chemical changes. Chemical changes are a little harder. They produce a new substance, and the identity of the substance is going to change. And you'll see things happen when a chemical change occurs. And we're going to do a couple examples of these in class. But for example, when a chemical reaction occurs, a lot of times it's associated with the release of heat. Maybe there's a popping sound. Maybe light is produced, or maybe bubbles are given off. Okay. We'll do a couple real simple ones of chemical changes in class. Okay. Flammability, reactivity. We talked a little bit about flammability. So think of burning a log. If I'm at a campfire, the physical change, if I want to take a log, is I cut it in half. I chop wood. I make the wood smaller. The chemical change is when I start to burn that wood. All right. There is a reaction that occurred, and flames were released. Light and heat are released in that scenario. All right, and then you're left with the ash and the stuff afterward. That is a chemical change of that wood. Rust, if you've ever seen rust, we've talked a little bit about rust before. Now, with chemical changes, there's this thing called the law of conservation of mass. Remember, matter and mass cannot be created or destroyed. So whatever the mass is of your substances before the reaction, it should be the same after the reaction. Okay. Let me go back to burning the bonfire, burning the piece of wood. When I burn that piece of wood, um, if I weighed that piece of wood before, it should be the same mass afterwards. And here's what I mean by that. After the reaction, if I take the gases that were released, if I take the ashes that were produced, I take the wood that's left over and put it onto a balance and get the mass, it should be the same as that piece of wood beforehand. Even though to us, when we look at that piece of wood, it's a lot lighter. Well, it's not just the wood now. There was all those things that were released that was part of that reaction. That goes into the law of conservation of mass. Okay. So there you go. That's kind of just the same thing I just said there about burning a log. That is a chemical change. With physical changes, we get back into properties of matter. This is something that we've talked about before. You guys already know the different states of matter. You have solids, you have liquids, you have gases. Um, I think these are things you've learned before, you've talked about before. A couple things to point out: solids. These are when the particles are tightly packed together and they have a definite shape and volume. So just again, think of a piece of ice. It has a shape and has a volume, you can measure it. Liquids, they have obtained more kinetic energy because they're heating up, right? Uh, if this solid to go from a solid to a liquid, I have to add heat to it. When I add heat to it, the particles start going faster. That's what turns it from a solid into a liquid, because those particles are speeding up. With liquid, they have a definite volume, but they don't have a definite shape. So they'll take the shape of the container they're in. All right. When we get to gases, again, the kinetic energy of those particles has sped up and sped up and sped up, and they start to basically escape that liquid because the bonds are not holding them together. All right. And we start to see vaporization. That's basically when the force between the particles um, has been overcome by the kinetic energy because they're moving so fast, and we start to see them becoming a gas. This happens in two ways. Evaporation, you guys probably know what evaporation is if you've looked at a black top. After it rained on a really hot summer day, you see that steam rising off the blacktop. That'd be evaporation. Or boiling. Boiling is when we take water and we heat it up to 100 degrees Celsius, it starts to boil. So solid, liquids, and gases are three states of matter. However, we have a fourth state of matter. Fourth state is, and I'll come back to this diagram, plasma. Plasma is actually in a lot of places, and it's actually the most common state of matter in the universe, even though it's not something that we can really deal with a whole lot. Um, it's basically a bunch of positively and negatively charged particles that are helping to form this. I'm not going to go too in depth with how it works, but think of these things that you see on the picture there. Lightning is plasma. A lot of plasma in the stars that are out in space. Neon signs. Aurora borealis. If you know what aurora borealis, this is all plasma. And the um, relationship between the positive and negative charges is what creates this. Says, well, big thing here is that it has such high energy that it strips electrons from atoms and it creates plasma. So it's very similar if we go all the way back to the start of the year when we say we were losing electrons to static electricity. This is like static electricity on steroids, right? So we're really stripping these electrons and creating this fourth state of matter. Found in the sun and all of the stars, lightning, neon, and fluorescent tubes. Now I want to go back to this diagram real quick, go back to my solids, liquids, and gases. Great picture here. Our solids are tightly packed molecules like ice, and this is when the molecules are moving slowly. Liquids, they are becoming faster. They're moving faster because we've added heat to them or kinetic energy to them. They start to move a little bit faster. Gases, they do not have a definite volume or a definite shape, and these molecules have continued to go faster and faster because of the heat added to them. Now, our next video, I'm going to talk about phase changes, and we're going to actually talk about a lab we'll do in class with the phase changes of matter.